Section 1611, Lewis acids and bases. For a substance to be a proton acceptor, which is a Bronsted-Lowry base, it must have an unshared pair of electrons for binding a proton. Ammonia, for example, acts as a proton acceptor. Using Lewis structures, we can write the reaction between a proton and ammonia as follows. G. N. Lewis was the first to notice this aspect of acid-base reactions. He proposed a definition of acid and base that emphasizes the shared electron pair. A Lewis acid is the electron pair acceptor, and a Lewis base is electron pair donor. Every base that we've discussed so far, whether it be a hydroxide, water, or amine, or an anion, is an electron pair donor. Everything that is a base in the Bronsted-Lowry sense, which is a proton acceptor, is also a base in a Lewis sense, an electron pair donor. In this Lewis theory, however, the base can donate its electron pair to something other than a hydrogen. The Lewis definition therefore greatly increases the number of species that can be considered acids. Proton is a Lewis acid, but it's not the only one. For example, consider the reaction between ammonia and boron trifluoride. This reaction occurs because boron trifluoride has a vacant orbital in its valence shell. It therefore acts as an electron pair acceptor, a Lewis acid, towards ammonia, which donates the electron pair. The curved arrow shows the donation of a pair of electrons from nitrogen to boron to form a covalent bond. Our emphasis throughout this chapter has been on water as the solvent, on the proton as the source of acidic properties. In such cases, we find that the Bronsted-Lowry definitions of acid to bases to be the most useful. In fact, when we speak of a substance as being acidic or basic, we're usually thinking of aqueous solutions and using them in terms of Arrhenius or Bronsted-Lowry sense. The advantage of the Lewis theory is that it allows us to treat a wider variety of reactions, including those that don't involve proton transfer, as acid-base reactions. To avoid confusion, a substance such as boron trifluoride is rarely called an acid unless it's clear from the context that we're using the term in the sense of the Lewis definition. Instead, substances that function as electron pair acceptors are usually referred to explicitly as Lewis acids. Lewis acids include molecules that, like boron trifluoride, have an incomplete octet of electrons. In addition, many simple cations can function as Lewis acids. For example, iron 3 interacts strongly with cyanide ion to form ferrocyanide ion. The iron 3 ion has vacant orbitals that accept the electron pairs donated by the cyanide ion. We'll learn more in 24 about which orbitals are used by the iron 3 ion. The metal ion is highly charged too, which contributes to its interaction with the cyanide ion. Some compounds with multiple bonds can behave like Lewis acids. For example, the reaction of carbon dioxide with water to form carbonic acid can be pictured as an attack by water molecule on carbon dioxide, in which the water acts as an electron pair donor and the carbon dioxide as an electron pair acceptor, as shown in the margin. The electron pair of one of the carbon-oxygen double bonds is moved onto the oxygen, leaving the vacant orbital on the carbon that can act as an electron pair acceptor. We have shown the shift of these electrons with arrows. After forming an initial acid-base product, a proton moves from one oxygen to another, therefore forming carbonic acid. A similar kind of Lewis acid-base reaction takes place when any oxide or nonmetal dissolves in water to form acidic solution. Hydrolysis of metal ions. As we've already seen, most metal ions behave as acids in aqueous solution. For an example, an aqueous solution of iron 3 nitrate is quite acidic. An aqueous solution of zinc chloride is also acidic, though to a lesser extent. The Lewis concept helps explain the interactions between metal ions and the water molecules that give rise to this acidic behavior. Because metal ions are positively charged, they attract the unshared electron pairs in the water molecules. It is primarily this interaction, referred to as hydration, that causes salts to dissolve in water. The process of hydration can be thought of as a Lewis acid-base interaction in which the metal ion attracts a Lewis acid and the water molecule as Lewis bases. Then the water molecules interacts with the positively charged metal ion, and electron density is drawn from the oxygen, as illustrated in figure 1615. This flow of electron density causes the oxygen-hydrogen bond to become more polarized. As a result, water molecules bound to the metal ion are more acidic than those in the bulk solvent. The hydrated iron 3 ion, which we usually represent simply as Fe3+, acts as the source of protons. The acid dissociation constant for this hydrolysis reaction has the value of 2 times 10 to the negative 3, so iron 3 is a fairly strong acid. Acid dissociation constants for hydrolysis reaction generally increase with increasing charge and decreasing radius of the ion. Thus, the copper 2 ion, which has a smaller charge and a larger radius than iron 3 plus, forms less acidic solutions than iron 3 plus. The case of A for copper 2 ion is 1 times 10 to the negative 8. The acid hydrolysis of a number of salts or metal ions is demonstrated in figure 1616. Note that the sodium ion, which has a large and has only a positive 1 charge, and which we have previously identified as the cation of a strong base, exhibits no acid hydrolysis and yields a neutral solution.